So today, in this session, we'll be focusing on differentiating between a vector and a scalar quantity, writing a vector in the form xy, finding the magnitude of a vector, and identifying equal, inverse, and parallel vectors. So Karima, I want you to look at this graph. Pay very keen attention, and then I want you to answer these questions. And you at home, answer these questions as well and see if you're getting them correct.
All right, I think I can do that.
All right, so can you describe this movement? Let me go again. Look at it. Boom. All right, can you describe that movement?
Using cardinal points?
Yes.
That looks like north, and it looks like 6 units north. Am I correct?
All right, so from here to here would be 1,
Yes,
2,
yes.
3, 4, 5, 6. All right, 6 units north. I'll take that.
I
How
hope my
about
geography teacher is
this
watching.
one?
That looks like 3 units east.
3 units east. Okay, so we have 1, 2, 3 units. All right, I'll take that.
All right, I feel bright this morning.
Can this move now be described in terms of east and north?
So that looks like the same 3 units east and 6 units north. So yeah, 3 units east, 6 units north.
So you would go 1, 2, 3 units east, and
Yes.
then 1, 2, 3, 4, 5, 6 units north.
Right.
All right, I'll take that. Is it possible to determine the distance covered in the final move?
I think so, I think so, but I'm hoping that we learn something more about that distance thing. Yeah, hoping that we learn some more about that for today's lesson. So I know it's possible, but I'm going to leave it until, later on.
All right, so viewers at home, you too can determine at the end of our session if it is that we can determine the distance of that movement right there. All right, so as stated, we're looking at vectors today. Now, what is a vector? Karima, what is a vector?
All right, well, you brought the answer right up on screen. I don't have to guess. So a vector is a quantity that has both magnitude and direction. So for it to be a vector, it must have both magnitude and direction.
All
Sounds
right.
interesting.
All right. Here
So
are some examples.
Yes, examples of vector quantities include velocity. I would have heard these terms before.
Right,
yes.
right.
Acceleration,
Vroom,
force,
vroom.
and one of my all-time favorites, bearings.
All right. I just want to ask this question real quick. What is a quantity with only magnitude called? Because it's a vector have magnitude and direction.
I think it's a scalar,
It is a scalar.
All right.
And then quickly, just example of scalar quantities: length, mass, and area.
All right.
One thing. All right. So Karima, you were saying about what's a vector and a scalar again?
Right. So we said a vector is a quantity that has both magnitude and direction. And when we talk about a quantity that has only magnitude, we're talking about a scalar, Latoya. All right?
Great.
So we have vectors and scalar quantities.
Excellent. So let's do a quick recap at home. So we're going to go through each of the quantities, and you're going to decide if it's a vector quantity or a scalar quantity. 5m, what say you?
That should be 5 meters.
5 meters,
Well,
sorry.
I am seeing magnitude, but I don't see any direction.
Okay.
5 meters in which direction? That looks scalar to me.
Scalar, all right. 30 meters per second east, what say you?
So I see magnitude and direction. So that must be a vector quantity.
There you go.
I feel bright.
5 meters north, what say you?
Again, I'm seeing magnitude, 5 meters, direction, north. Sounds like a vector quantity again.
Perfect. 20 degrees Celsius. I think you have this one.
Looks scalar to me.
Scalar indeed. 256 bytes.
seeing on the magnitude again, that looks scalar.
4,000 calories, something we should not be having.
I was about to say that, you know, scalar.
Scalar indeed. All right. Now, did you know that vectors are used to determine the duration of a voyage, as well as to tell on which country a ship will make landfall? Did you know that?
That sounds interesting, Latoya. And
Yes.
I'm seeing here where it says captains use vectors to determine wind speed and direction, ocean current, as well as the velocity of the ship. And the journey is the result of all of these vectors.
It is indeed, and here is an image, because we don't want you to think that when we're doing math, it's just all math and boring real life stuff.
I wonder if that's what Christopher Columbus used.
I was wondering the same thing.
So we're seeing here where the red vector is showing the ship's velocity, and that is the path that the ship would take, you know, if there weren't any interference from ocean current and wind speed. But as we look at the diagram, we're seeing that blue vector for ocean current and that green vector for wind speed and direction. And so with those affecting the ship velocity, we're seeing that black vector now, which is showing the ship's actual movement. So, you know, it's possible that a ship was leaving Spain, trying to head to the United States, but with ocean current and wind speed and direction, the ship
end up at, where is that now? Hispaniola? Don't
yes,
quote me.
somewhere between Haiti and Dominican Republic.
Somewhere there.
Yes.
All righty, good stuff.
So vector is very useful.
All right. So I wanted to pay attention to my grid again. And vectors can be represented graphically using an arrow, as you are seeing on your screen here. And we're calling this vector AB. We're naming our vector AB. This vector shows a movement from A to B. So we are going from A being here, and we're going to B as indicated on our vector by the arrow there. And so if we're writing vector AB, we write capital A, capital B with a little arrow at the top showing that we're going from A to B.
So Latoya, that arrow at the top is very, very critical.
Very critical.
Yes, because it's showing us, you know, that movement. What's the start point and what's the end point of this movement.
Perfect.
All right, so the length of the arrow indicates the magnitude of the vector. So pretty much when we draw our vector on a grid, you know, using these arrows, the magnitude speaks to the length.
I was just about to say, I've been hearing this word magnitude.
All right. So
and what if I don't know what magnitude is? So when we talk about magnitude, we're talking about
the length of the representation that we have there. And of course, it says the direction of the vector is represented by the direction of the arrow. And you'd have pointed that out earlier.
Right.
So I could not look at this vector and call it vector BA, because when I look at the arrow, I see that it's not a movement from B to A, but rather it's a movement from A to B. So direction is so important.
All right. Can you now describe the vector shown in terms of horizontal and vertical components? So, which we would have done earlier.
Yes. I wish you could touch the screen for me, Latoya.
Definitely.
Right. So when I'm moving from A, I'm going to see a horizontal movement of 1 unit.
Okay.
Yes. And then I'm going to be going up. That's vertical. And that looks like 4 units. So 1, 2, 3, 4.
All right.
All right. So horizontal component 1, vertical component 4.
Okay. All right. Let's see. 1.
I'm right. I'm right.
4.
All right. Great.
All right. I was just about to ask, and then it came up. Why couldn't I look at the movement upward first, instead the vertical movement instead of the horizontal movement first?
Well, we're looking at this now as it came up on screen. The vector can be written in the form xy, and you know, x there represents our horizontal movement.
Right.
In other words, that movement is parallel to the x-axis. So we're moving similar to how our x-axis moves, yes?
Right.
And the y component speak to our vertical movement, and so
Right.
that would be parallel to our y-axis.
Y-axis.
All right.
X-axis. Okay.
Beautiful.
So we always have to take into consideration our horizontal
Horizontal.
movement
Yes.
first, and then our vertical movement. And I have a dance coming up for you.
Oh, dear Lord, save us.
All
Right,
right.
so we would have covered that
Right.
part.
So, can you now tell me what would be the vector in the form xy for vector AB?
I'm sure our students can tell us
Can
that.
you tell me?
Yeah.
Write it down. I'm waiting. I'm looking. Let me see. You don't write it yet. Write it.
I think that's 1-4.
Okay.
Yep.
1-4.
All right, 1-4
Good
it is.
job. All right. Now here's an activity. Parrot Morgan hid his treasure and left this map as a guide to the treasure. To prevent persons from finding the treasure, he gave part of the route as vectors. For another part, he drew the route, which you must describe using a vector.
So it seemed as if Parrot Morgan, really didn't want anybody to find his treasure.
Which
He called up the thing.
are we going to find it
Of
anyway?
course, we're mathematicians. So.
And we're Jamaicans. We go find
okay,
it.
here goes.
All right, so from start point, you're going to travel along the vector 2, 5. So
All
we're
right, so I'm
starting
seeing
here.
Start, yes. So
And
2, 5.
So where you think we'll end up if we're starting here and we're moving along the vector 2, 5?
Well, I know that 2 is a positive 2, so we want to speak a little bit about that, Latoya, because
Yes.
the 2 is saying to me, yes, we spoke about it being movement parallel to the x-axis, but we also want to focus on, is it left? Is it right? How am I moving? And so that positive 2 is saying I should move 2 units to the right. All right.
And then the 5.
And the 5 now, remember we spoke about vertical movements, and so, but am I moving up or down? So I'm going to look at the positive 5, and so that is saying to me that I'm moving 5 units up.
And if we think about our Cartesian plane, the positive units would be going upward and rightward on our Cartesian plane.
Right. Makes sense.
All right, so here we go. 2, 5 from the start to our little tower here. So 1, 2,
Yes.
1, 2, 3, 4, 5.
Beautiful.
All right, there we go.
Parrot Morgan thought he could fool us.
No, he can't.
All right.
All right, then. So then it is now saying that from here, the lighthouse, we should now travel 3, 2. And as we discussed just now, the 3 and the 2 are positives, meaning that we're moving 3 to the right because we do our horizontal movement first,
Yes.
and then 2 upwards.
All right.
So here we go.
Okay.
All right, now this is saying give the vector of the movement shown with the broken lines. All right, so we're moving from the car now to the, I'm going to say the apple trees.
All right. Could be a forest. Who knows? But yes. So I'm looking at this, Latoya, and I'm seeing the horizontal movement is a rightward movement. So I see that that's positive 1.
Right.
But then I'm moving downward, and it's 3 units down. So that vector looks like 1, -3. Am I correct?
All right, let's see.
I'm just on the ball this morning.
Brilliant. All right, how about now we're going to travel along the vector -2, -1.
-2,
Negative
-1.
one.
All right, so I see -2, meaning I should move 2 units to the left.
Because we do our horizontal movement first.
Yes.
Right.
And then I'm seeing -1.
Right.
Which means I'm moving down
Right.
1 unit. That looks
All
like
right.
it should take me to the castle.
So let's see, you said 1, 2, and then 1.
Yes.
Let's see. There you go.
Great.
All right.
So I see an instruction there that's asking us to write
Write
down
down
the
the
vectors for the route. So let's start with the starting point.
So that's 2, 5.
All right, so Latoya, you read for me and I'll just
3, 2,
jot them down.
1, negative 3, negative 2, negative 1. Viewers at home, ensure that you're writing down your vectors as well, because you're going to need this information for our next activity. All right? Now this is saying, can you state the vector for each part of the return journey? So if I'm returning, it means that I will have to now go back where I'm coming from, right?
Pretty much, yes.
So the last place I was at the castle here.
Correct.
And I came to the castle from the
Apple
forest
trees.
tree.
All right.
All right. So what was our vector for what was our last vector again?
Negative 2, negative 1.
Okay, so if I want to now go from the castle to the tree, how would I get there?
So we need to still do our horizontal movement. And I'm
Okay.
seeing now that I'm now moving right.
Okay.
So that's now a positive 2. So let me write that down below this one. Positive 2. And I'm moving 1 unit up. And so that's positive 1.
All right, let's see. So from here to here, that's 1, 2, and then a positive 1.
Yep.
Brilliant. Okay, so now we are going from the tree to the car, I'm assuming.
And so that looks like...
What was our original vector from the car to the tree?
1, negative 3.
Okay, so how do we move from the tree now to the car?
All right, so I'm seeing a leftward movement of 1 unit. So that's negative 1. And I'm seeing an upward movement of 3 units. So that's positive 3.
All right, let's see.
I hope our students are
Negative
writing down
1,
these vectors.
positive 3. That's what you said?
Yes.
All right. So now we want to move from our car to the lighthouse. What we had initially. What did we have initially?
We had
what
a
did you
vector
have?
3, 2.
Okay. So if we are going in the opposite direction now, we're returning. What's that?
Interesting. I like that word that you use, opposite. We'll talk about it in a minute.
Right.
So horizontally, I'm moving 3 units to the left. Yes, and 2 units down. So that's negative 3, negative 2.
All right. Now we're going back to the start, going back to the boat because we find the treasure and we want to go home now.
I know, right?
So how do we get from the lighthouse back to the boat, back to home, so we can sort out the treasure, call grandma, call mommy,
And divide
share
up the spoils, yeah.
Everybody get them piece.
So we have 2 units to the left. So that's negative 2. And we have 5 units down. So that's
So
negative.
you said left is, okay. 1, 2, 1, 2, 3, 4, 5. And I'm
Yeah.
back to my boat.
So you would have used the word earlier, Latoya.
Excellent.
You spoke about opposite, and we're asking our students
Yes.
in television land, what do you notice about these vectors? So they have been written on the board, and so I want our students to pay keen attention to what's happening on the board. So I've written at the top part our vectors for the journey to the treasure, and below that we have the vectors for the journey back to the boat. And I'm looking here, Latoya, and I'm noticing that where I had negative 2, negative 1, I now have 2, 1. And where I had 1, negative 3, I have negative 1, positive 3. And I'm kind of seeing that pattern. Yes. I seen that pattern coming out. And the word that you would have mentioned, opposite.
Opposite, right.
So we notice that these vectors, the direction, they are opposite. So while this vector took me from the trees to the castle, this vector here would take me from the castle back to the trees. So I'm seeing opposite directions taking place. And there's a word.
There's a word.
Starts with an I.
Indigo?
Inverse, girl.
Inverse.
Sure.
Inverse.
Inverse. So we're saying that these vectors are the inverse of each other.
Yes,
all
they
right?
are indeed.
And we'll talk a little bit more about that
yes, they
in
are.
a few.
All right. Now, after finding the treasure, you decided to take the shortest road because you can't bother with the go round story, come back round part.
Excitement, girl. Why take the long road home?
To get from the castle to the boat. No. from looking at our map, what would now be the shortest distance from the castle to the boat? So initially we went up, so round, so down, so instead of doing all of that, I don't need to go back to the tree, the car, and the lighthouse. Come find something already. So I just now come straight across here, so.
Makes sense.
And there you go. Voila, I reach at the boat.
Indeed. Such a short
But
distance.
it is now asking me to calculate the distance from the castle to the boat. Now, initially we were counting.
Yes.
But now this is slant.
Yes, and so we need to find that distance.
Right,
Looks
so
a bit tricky to me, you know.
How do
A
you
little bit
think we
tricky.
can find the distance from the castle to the boat?
I'm thinking
Think
though
about
that
it.
there are some things that we need to consider.
Right.
You know, when we're looking at this particular question.
Yes.
You know, so first of all, can we represent or can we look at the horizon? Jeez.
Can we think alike?
Can we identify the horizontal and vertical components of this movement from the castle
All
to
right,
the boat?
horizontal and vertical. Okay, so horizontal first. That
Right,
would have
so-
been here.
Yes.
And then I now go downward to the boat.
Right, so we move left, which is negative
Right.
4, so I want to
Yes.
point that out. And then I'm moving downward,
Yes.
which was downward movement of 3
Yes.
units, so that's negative 3. So I'm just going to write that
So we
on the
have a
board
vector
quickly.
of negative 4, negative 3.
All right, and they're asking us to find the distance.
All right. Now with the shortest route formed or decided upon along with the vertical and horizontal components, I am seeing a triangle.
I am seeing it too, that's why I'm trying to
A
represent
right
it on the
angle
board.
triangle.
And I want to point out that this negative 4 and this negative 3, just want to point out because I don't
Yes.
want anybody to think that this is a distance, because we know distance is
Cannot be
not
negative,
negative. So
right.
this negative 4 is representing the movement that we made,
Right.
which we said is a leftward movement.
Right.
And so we're representing it with a negative 4. And the 3 here was a downward movement, and so we're representing it with a negative 3.
Something just came to my mind. So that means that when we have the negative portion of the numeral is telling us the movement.
Yes.
And then the positive is telling us the movement. So it's not that the numeral is negative, but it's
So, hold
describing
on.
the movement.
Yes, you're just getting that?
Kind of.
Okay.
I'm slow sometimes. I don't have
Okay.
breakfast yet.
All right.
Sorry.
So I'm
You
seeing the
know?
right angle triangle though, and I want our students to think, because there must be a mathematical idea that
Yes.
comes to your mind whenever you see a
A
right
right
angle
angle
triangle.
triangle.
Especially when you would know these two components of that right angle triangle, and you're being asked
To find
to find the length of
the hypotenuse.
Girl, you couldn't let me ask the question.
Gee, sorry.
All right, so the length of the hypotenuse,
You're
that's
welcome.
where we are, the length of the hypotenuse. So, what mathematical idea came to your mind? Your mind?
My mind. Math. Idea. Triangle.
Today.
Love. No, that's not a mathematical idea.
Pi
Pythagoras theorem. There you
All
go.
right, so Pythagoras' theorem would come to mind, yes?
Yes.
And so
it's right angle, yes.
I'm thinking we can use that.
All right, use
so
it then.
Let's speak a little bit about Pythagoras' theorem and what he says. Now, our students would have been familiar with this representation of the theorem. And basically, what this is saying is that our hypotenuse square,
Yes.
we obtain that whenever we square the lengths.
Yes.
And in this case, we're looking at the movement. So whenever we square that, those two shorter sides,
Right.
and whenever we find the sum
Right.
of those squares, it will give us the square of the hypotenuse.
Well, this is perfect for us.
Perfect.
Because we have the other two sides and we want to find the hypotenuse.
All right. So bearing in mind that these are movements,
Right.
just want to ensure that that point sticks.
Yes.
Because we don't have the length of a side being negative.
No, we don't.
All right. So let's go with. So I'm squaring negative
Right.
4. and I'm also squaring negative 3. I'm
Right.
going to call this, I'm going to stick with the C for now.
Right.
All right? So what's the square of negative 4?
Well, that's 16.
16. All right. And the square of 3 is?
9.
9. And 16 plus 16 when it's added
Call
to...
yourself the bigger number, so that's 16.
All right, so 25, I will not wait on you.
Okay.
No, that would make me a bad teacher.
Okay.
All right, let me wait on you.
Count on your finger if you need to. Okay.
Let me wait on you. So
I ain't
16.
judging.
So when 9 and 16 are added,
Right.
we get 25.
25.
All right. Now, interestingly, we want the length of the vector.
Right.
They
and
didn't
it's-
ask us about its square, did they?
No.
So
we
how
now
do I
want
get
C?
How do I get C now?
So, so we're
back
doing
side?
the opposite.
All right, so we're doing the inverse. Inverse
Right.
of square is
Root.
Square root.
Square root.
All right.
Right.
So I'm gonna be square rooting or finding the
Because
square root.
balancing our equation here, anything you do to one side, you have to do to the other.
Okay, I hope we're seeing this. I hope this marker is bright enough. So I'm seeing here that C, which is our vector,
Yes.
would be equal to 5
5
units. So it
units.
would have a
Wow.
length of 5 units. But I want to make a distinction quickly here because we have looked at A and we have looked at B.
Right.
But then when we are writing our vector, we are writing it in terms of X and
And
Y.
Y, right.
So I could probably, replace these for now with X because this is our
Right.
X component, and I could put
Y.
Y there,
Right.
yes. And would have noticed that we square rooted here.
Right.
I want our students to see, because sometimes we see some formula in books and we're not so sure,
What
how it
it
came up.
means, right?
Right. So if I'm finding C square, then it's X square, or let me just put this now. All right, so let's leave it at C square for now.
Right.
So X square
Or we could just give the vector a name.
plus Y square, so name it V. All right, so X square plus Y square. And we said in order to get C,
we square
we
root,
square root
both
sides.
sides.
Yeah?
Right.
So let's call the vector V for
V,
now.
right?
All right, so in order to get V, it's the square root of X square
Plus Y squared.
Y square. And so you might see that
All right, so what we're finding here is the magnitude of the vector.
good,
So
and I'm going to talk about this symbol here now,
Right,
because
right,
sometimes when we get to the exam,
Right.
we see these symbols and we're not so sure what
What
they
it
mean.
means,
So
right.
this is actually referring to the magnitude of the vector.
Right.
So you may see this formula, so let me write it out quickly.
Mm-hmm.
Magnitude of the vector, and that will be equal to, we would square the X component
plus the
square
Y
the Y component, we add them, and then
voila.
square root, and then voila.
All right. So as you would have said rightly, my dear, when we're talking about the magnitude of a vector, it is indeed the square root of the square root of the sum of
Yes.
the X component squared plus the Y component squared. And in this case, it was -4 and -3.
All right. So I
All
think we
right.
can move on now.
Okay. So here we have some vectors. And we're zooming in a little bit on vectors R and T. Can you identify a relationship between R and T, Karima?
Well, I'm looking at R and T, and you said
Right.
that the arrow tells the direction.
Okay.
So they look like they're going in the same direction to me.
Uh-huh. They are.
And magnitude, we spoke about that earlier. So
Yes.
let's see what the X
In terms of the
component-
length of the vectors.
Right.
To me, it looks as if it's the same length. However, in math, we don't assume. We prove.
We prove.
Right? So
All
let's-
right. So
let's see if we can prove.
See if we can find the magnitude, and I'm putting in the symbol there
Right,
for
of
the
R.
magnitude. And my horizontal component is 1.
Mm-hmm.
And using up my formula, so let's put on my square root quickly. So the X component is 1, and I'm squaring that. And the Y component is 2, and I'm squaring that as well. So the magnitude here is the square root of 1 plus 4. So that now becomes the square root of 5.
And we could leave it there.
We
or it
could
be 2.23, I think.
All right,
R.
so
You have 2. Square root of R. I mean, yeah.
yeah, the modulus of R. All right, so that would be 2.2, and I'm putting it to 3 decimal places for
Units.
now. Units.
So, just to note, if you were not given a particular unit, if we're determining the magnitude of a vector, we still have to say units.
So we say units, right?
All right. So, that's
look,
R.
That's R. But then when I look at T, though, I'm seeing the same 1 horizontally, and I'm seeing the same 2 vertically.
1, 1, 2. Okay.
Yes, that's R you just looked at.
Yes.
So do that for T for me.
1, 2. 1.
Yes. 1, 2.
There
cool.
you go. Short.
So it looks to me like they are the same length.
So they have the same magnitude.
Direction. All right, you go ahead.
Same direction. Same magnitude.
That makes them equal. Equal it is.
Equal?
Equal, yeah. Equal.
All right then.
Right.
Well, this is saying that vectors R and T are equal.
Yep.
And vectors with the same magnitude, so that means that vectors with the same magnitude going in the same direction, we call those vectors
equal vectors.
Excellente. All right. What about, is there any other relationship that you can find between vectors R and T?
Well, they look parallel to me, but I'm going to leave that one a little bit, but they look parallel to me. Just by looking.
They look a little equidistant apart.
Yeah, and they're on a grid, so it's accurate. But we'll talk a little bit more about that parallel thing.
Okay, no problem. All right. How about vectors R and U?
Well, we found R already, so I think we just need to check U and see what those components are.
I'm seeing U going in the other direction.
Opposite?
Opposite direction.
Okay, and we talked about inverse vectors earlier.
Yes,
so tell me about the components now, though, because it's going in the opposite direction, and so my horizontal movement is now a -1.
Right. So I'll have to go from here to here. So that's 1 movement to the left.
Right.
And then 1, 2 downwards.
Right.
So that's
-2 as well.
Okay.
So let's just nice this up quickly and see what's happening. What happens though when I square -1?
We get a positive result because we're multiplying two negative numbers.
1?
Yes.
So I see 1 there. What about when I square -2?
I get +4.
+4. It looks to me like they have the same magnitude. What do you think, Shariah?
I think so. But then again, guess what? Guess what now? So R is going upward. I'm going to say upward for now. U is going in a downward direction. But they have the same magnitude.
Well, a while ago we said vectors that are going in the same direction
with the same magnitude
are equal. So now we have same magnitude but different direction. So they can't be equal. But we would have used this term before. There must be the inverse. Didn't we talk about this? Yeah. Bring it up. Bring it up on screen, girl. I feel bright this morning. So they are not equal, but so what do we say?
They are
the inverse of each other. So R there, as you can see on screen, R is equal to -U.
And negative meaning
now
the
to
direction.
Beautiful.
Everything are coming together, man.
Nicely.
Are you paying attention?
And we have a little
You're getting it? I hope you're getting it, you know. Write down everything.
All right, so let's move on quickly. We're seeing time.
How about R and S?
R and S, well, clearly, those are not the same magnitude for sure.
No, not the same direction either.
Not the same direction either. But when I look at that though, Shariah, I'm seeing where vector S looks like it's twice vector R.
We don't assume,
but we don't assume, not true.
So what's the
So let's look at that quickly.
So we know that it's going downwards, so we go 1, 2. So that's -2 for X component, and then 1, 2, 3, 4. -4 for Y component.
All right. So let's quickly set that up. So the magnitude of S, what is 2 squared? -2 squared, sorry, that's 4. 4. And -4 squared
16.
will give us 16. 16 squared will give us 24. 24 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 So that's the square root of 20. I'm so happy I worked this out earlier. And so I am seeing here that this would actually be 4.472 units.
All right. So
I'm 100% sure that I'm right when I say that vector S is twice the length of vector R.
okay.
And we said they're going in opposite direction.
Okay.
Cool?
So S and R in opposite direction, and S is twice R, as you said.
Yes.
So that means that S is actually negative 2R.
Right, and that
Or-
negative speaks to direction being
Right.
different, and 2 there speaking to the magnitude being twice.
Right. Or
Right.
we could say that R is negative half of S.
Makes sense.
All right. So that means that they're parallel.
Yes. And we said
And
we were going to talk about parallel.
Right.
You know, so it says here that 2 vectors are parallel if they are scalar multiples of each other. So, so much important information is on the board. I really didn't want to erase. So we compared vectors R and S earlier. Well, R and T earlier. We also compared vectors R and U. And just now we did R and S. And we said that 2 vectors are parallel if one is a scalar multiple of the other. If they're scalar
and
multiple.
multiple.
All right, so that's why I wrote this on the board, Shariah. So I'm seeing here that R is equal to T. Yes, so R is the same as 1T. So the scalar here is 1.
Okay.
Yes, so remember we
Okay.
said scalar just have magnitude. So
Right,
it's
right,
so
right,
it's a-
right.
So here, vector R is equal to negative U. And
that's
so that's negative 1.
U. Okay.
And then we
okay.
said R is equal to negative half S.
Okay, so
negative
scalar
half
and
is now the
multiple.
scalar.
So I'm putting those 2 words together, scalar and multiple. So scalar is a real number.
And it's multiplying.
It's a multiple of
Or
the
it's
other.
multiplying that vector.
All right, so that means that R, S, U, and T are parallel.
They are all parallel.
They are all
And
parallel.
time is really up on us.
All right, then.
So we're just gonna look at this question. It spoke about vectors A, B, and vectors D, C. And you know, Shariah, I think we're gonna be picking up on this question for the next lesson. Look at it, viewers. Take a picture and see if you can answer this question based on what we would have covered
Get to do
today.
My dance.
Oh, Lord, you are still alive. You saved me from this dancing girl. That's all today for CSEC Mathematics Introduction to Vectors. We hope you grasped most of the points we discussed.